In our previous video, we looked at range and interquartile range. We even created a box plot from that interquartile range. So let's wrap up our discussion about measures of dispersion or variability with the last three, which is standard deviation, a variance, and our coefficient of variation. So standard deviation measures the variability by comparing each data to the mean. So whether we're analyzing the standard deviation of the population, so we're going to divide there by the population size, big N, or the standard deviation of the sample, and we would then divide by little n, the sample size, and then we would adjust that sample size here. We call this degrees of freedom. See how there's this n minus 1? And that is to recognize the fact that we have here that we have made an estimate, a summary of the sample, and then we are using that to measure this sample statistic. So there's this little adjustment here for the fact that this summary depends on that summary, and it's all the sample. So what we do is we look at how far each data point is from the average for the sample. We take those distances and we square them, and then we add them up and divide by n minus 1. to get the standard deviation. What this tells you is how far are the data points typically from the mean. Okay, and you could find it for the population, you could find it for the sample. So let's suppose we have these particular numbers, 62, 68, 74, and 76. To calculate the sample mean, that'd be the first step. We find the average of those four numbers. Then what we're going to do is we'd find the difference from them. So let's just pull our Excel back up here. Oops. Pull this down here. Okay. 62, 68. And you can't see those. Those are super tiny numbers. So let's make this way bigger. 68. All right, 62, 68, 74, and 76. So if you're going to find the standard deviation, the first thing you would do is find the average of your four numbers. There we go. So the average here is 70. You would then need to find the difference between your number. So this is the x minus x bar part of the formula. So we would find how far each one is away from that average. Okay. And then what we would do is we would take that information and we would square it. And then we would add it all up. And divide by n minus 1. 3 minus 1. Okay. So calculate the sample mean. For each observation, calculate the difference between the data value and the mean, square the difference, sum them up, divide by n minus 1, and then the last thing you do is take the square root. SQRT. That's a lot of steps. We get 7.745. Now, you can just have it tell you the standard deviation of your numbers in Excel. Okay. Notice that these are slightly different, and that's because this is the standard deviation of the sample. This is the standard deviation of the population. So you technically want ST. So there's a P and there's an S. That one is the sample. That one is the population. You can see how the formulas were slightly different. So we technically want this one. We still get completely different numbers. All right, why am I getting different numbers? Because this should not be 3 minus 1. This should be 4 minus 1 because I have 4 sample sizes here, and I was automatically subtracting 1. So 4 minus 1, we get 6.32. So just to show you, this is stdev.s, that's the sample one. stdev.p, that, and then stdev, the old one. Should still be the sample one, I think. Yeah, there we go. Okay, so just be careful about which formula you're using. stdev.s is the sample formula. stdev.p is the population parameter. If you're using the old stdev, it is the sample one. So I stand corrected from a second ago. It is the sample one. So that one is okay too if you're using the old formulas. So there is difference here in whether you're calculating the standard deviation for the population or the sample. Standard deviation is the most widely used measure of dispersion. We like it because it's mathematically tractable. When we do other formulas, like for our hypothesis testing, we'll use standard deviation in our calculation. Downside is it's more sensitive to extreme values than the range. Not as much as the range, but more than the interquartile range. The benefit of using it and why we like it, in addition to mathematically tractable, is that it is stable. So when you do multiple samples, you're going to get standard deviations that are very similar to each other. Whereas the range, for example, is quite different every time you take a different sample. The variance is the standard deviation squared. So you'll notice there's no square root. Whether you're looking at the variance of the population here, this is the same formula as the standard deviation of the population, just without the square root. The variance of the sample is the same as the standard deviation, just without the square root. So variance gets rid of that square root. The standard deviation is easier to interpret than variance, but variance is more of what's in your other calculations. The last one we'll look at here is the coefficient of variation. The coefficient of variation is looks at the amount of dispersion relative to the mean. So what it does is it takes the standard deviation and divides by the average. So we'll use the coefficient of variation to compare dispersions between two distributions that have different means. And so the challenge, of course, is that if you have two different measures of central tendency, two different centers, then knowing how much spread there is can be difficult. So the coefficient of variation looks at the standard deviation relative to where that mean or center is. So it allows for comparison between two different distributions with different means or two distributions with different units of measurement. Because the other challenge is if you're trying to compare variability and one is in inches and one is in centimeters, they're of course going to have different variability because of the units you're measuring it in. So by standardizing it, by dividing by the average, it helps for that comparison. An example of the coefficient of variation is this example here. So let's say we have 4 pulse rates, 62, 68, 74, and 76. The average is going to be 70. The standard deviation, if we look at how far each point is from that average, square it, divide by n minus 1, take the square root, we get a standard deviation of 6.32. So for those pulse rates, the average is center. On average, everything 68% is within 6.3 each direction of that, right? So majority of the data is between 76.32 and 70 minus 6.32, so 64-ish. The coefficient of variation would take that standard deviation, divide by the average, and you get a coefficient of variation of 9%. Now let's say we compare another set of data. So 4 pulse rates. This one's 50, 65, 89, 62. Automatically we see there's a much wider variability in the responses. The average itself is lower at 66.5, but the spread is bigger too. The standard deviation is 16.34. Now the averages are different. The standard deviations are different. Here the measurement units are the same. But if we want to be able to compare these two, we can take that coefficient of variation, take the standard deviation divided by the average, and the coefficient of variation for that second data set is 25%. It's a bit easier to see that there's more variability in the second data set than the first. If these were completely different units of measurement, we would especially need that coefficient of variation in order to compare the two. So you can see already the mathematical tractability of standard deviation, right? It's in this formula. We can use it for other things. So coefficient of variation just helps us standardize when we're comparing two different things instead of just comparing the standard deviation straight. Variance is the standard deviation squared, so we get rid of having to deal with that square root. But standard deviation, it's the most popular because we can interpret it as how far away typically are the data points from the average, from the center. And it gives us the empirical rule, which we'll talk about later, which is within one standard deviation of that symmetric distribution, 68% of the data lies. And within 2 standard deviations, 95%. And within 3 standard deviations, 99.7%. So it can help us in terms of normalizing or standardizing our data as we analyze the impact the different variables have on other variables or the relationships between them.